You know that we are trying to construct Euclidean plane geometry from scratch. In the previous video, we looked at undefined terms and defined terms. In this video, we are going to look at axioms. Now, what are axioms? Axioms are statements which are accepted to be true without proof. They do not surround themselves with doubt or controversy, at least within that particular field of study. Now, we are going to study 8 axioms which were originally described by Euclid and 3 other important facts. Let's look at the first axiom of Euclid. What is the first axiom? The first axiom is, between any 2 points, one can construct a single line segment, and this single line segment is unique. So, let's consider these 2 points. Between these 2 points, we can construct a single line segment. This line segment is unique. You cannot construct 2 different line segments between these 2 points. That is what the first axiom says. The second axiom says, this line segment between any 2 points can be extended indefinitely on either side. So, you know that this line segment has a finite length, right? Now, we can extend this on either side indefinitely, right? Okay? That's what the second axiom says. The third axiom says, if any 2 points are given, one can construct a circle such that the radius of the circle is the distance between these 2 points. Okay, let's call this point A, let's call this point B. Okay, if we take point A as the center of the circle, we can construct a circle like this. If we consider point B as the center of the circle, then we can construct a circle like this. But the radius of the circle is the same. Okay, I know they don't look like circles, but imagine that they are circles, right? So this is what the third axiom says. It's pretty basic stuff, right? Now, let us see what the fourth axiom says. Now, consider these 2 lines. Now, think of a third line which intersects both these 2 lines. We will call this line a transversal line. A transversal line. As a result of these intersections, 2 pairs of internal angles are formed on either side of the transversal line. We call this alpha, this angle alpha, this angle beta, this angle theta, and this angle gamma. Okay, so one pair is alpha and beta, and the other pair is theta and gamma. Alpha and gamma are on the right side of the transversal and theta and gamma are on the left side of the transversal. The fourth axiom says, if two lines are intersected by a transversal and if the sum of internal angles on any one side of the transversal is less than 180 degrees, then the two lines will meet each other if extended far enough on that same side, right? If two lines are intersected by a transversal and if the sum of internal angles on any one side is less than 180 degrees, then these two lines will meet each other on that same side if extended far enough. Now you can see that the sum of alpha and beta seems to be less than 180 degrees, right? They seem to be less than 180 degrees, right? So we will extend these two lines to the right. Okay. You can see they meet here. Right? They meet here. That is what the axiom says. Okay? Now in Euclidean plane geometry, this fourth axiom is given the honorary title, the axiom of parallelism. The axiom of parallelism. Parallelism. Why is it called the axiom of parallelism? Now imagine that the sum of alpha and beta is not less than 180 degrees. Are these two lines going to meet one another if extended to the right, far enough to the right? No. What if the sum of theta and gamma are also not less than 180 degrees? Are they going to meet if extended far enough to the left? No. These two lines are not going to meet one another if extended to the right or left, which means by definition that these two lines are going to be parallel. Okay, they are going to be parallel, right? That is why it's called the axiom of parallelism. Let's have a look at the fifth axiom. Now consider any two magnitudes of the same kind. What I mean by any two magnitudes of the same kind is that A and B can be any two lengths, any two areas, or even any two degrees. If A is a degree of some angle and B is another degree of some angle, or A is some length of a line and B is the length of another line, okay? That is what is meant by any two magnitudes of the same kind. Then there are only three possibilities. Okay, if A and B are any two magnitudes of the same kind, then there are only three possibilities. A could be equal to B, A could be smaller than B, or B could be smaller than A. Okay, these are the only three possibilities. Can you think of any other possibility? I don't think so, right? So that is why it's called the fifth axiom. The sixth axiom. Let A, B and C be any three magnitudes of the same kind, right? Any three which means A, B and C can be any three lengths, any three areas or any three degrees. Okay, then if A is equal to B and B is equal to C, then invariably A is going to be equal to C. Okay, if A is equal to B and B is equal to C, then A is equal to C, right? I hope you all agree with this, right? It's common sense. So this is the sixth axiom. Now we are going to look at the seventh axiom. Let A, B and C be any three magnitudes of the same kind. If A equals B, then the sum of A and C is equal to the sum of B and C. What it says is, if A and B are equal quantities and you add equal quantities to both A and B, they are going to be the same. The result is going to be the same. Okay, that is the seventh axiom. The eighth axiom, it says, if A, B and C are any three magnitudes of the same kind, and if A equals B and C is smaller than both A and B, then the difference between A and C is equal to the difference between B and C. I have added this phrase because otherwise this is if C is larger than A, this is going to be negative. A magnitude cannot be negative. We are not talking about negative magnitudes, right? So to make this positive, I have included this phrase, C is less than both A and B, right? So what it means is, if A and B are similar quantities, if we subtract the same quantity from same quantities, the result is going to be equal, right? The difference between A and C is going to be equal to the difference between B and C. That is what it says. Now we have completed the 8 axioms which were originally described by Euclid. Okay, now we are going to look at 3 other statements, right, which are essential for us to continue our journey, right? We need these 3 important statements to prove certain theorems in plane geometry, right? They are not really axioms, but we will include these 3 statements here. Okay, the first statement is, if A, B and C are any 3 magnitudes of the same kind, right? If A is less than B, then the sum of A and C is going to be less than sum of B and C. You can prove this. Actually, in the section on arithmetic, fundamentals of mathematics, we proved this, right? So this is not exactly an axiom, okay, but we must know about this if we are going to prove certain theorems, in some basic theorems in Euclidean plane geometry. I think there is no controversy, right? You can understand that. Now you know that A is smaller than B. Now you add similar quantities to either side. What's going to be the result? Of course, intuitively you know that A plus C is going to be less than B plus C. Okay, so that is the first statement. Okay. The second statement is if A, B, C are any three magnitudes of the same kind, if A is less than B and if C is less than both A and B, right, then the difference between A and C is less than the difference between B and C. Okay, you know why I have included this, not to make these magnitudes negative, right? So what it says is, if we subtract C from both A and B, the difference between A and C is going to be less than the difference between B and C. This is not an axiom, but we need this. So I think there is no controversy here, right? Your intuition says that this has to be correct. Finally, we are going to talk about the axiom on triangle congruence. It is not exactly an axiom, it's a statement, right? It's just a statement, but we have to start somewhere, right? So we will call it an axiom, okay? So when we say two polygons are congruent, what we mean is they coincide exactly when superimposed. So if any two triangles possess this criterion, then they are going to coincide exactly when superimposed. They are going to be congruent. So what is this criterion? It says if any two triangles share two sides and the included angle, they are going to be congruent, right? Let's say this is triangle A, B and C, and this is triangle D, E and F. They don't look really congruent. Okay, right? D, E and F. Okay. If AB is equal to DF and if AC is equal to DE and if the angle CAB is equal to the angle EDF, right? If AB is equal to DF and if AC is equal to DE and if the angle CAB, okay, is equal to the angle EDF, right, then the triangles ABC is congruent. The symbol that denotes congruence is congruent to the triangle DEF. Because we are talking about the included angle between any two given sides, we call this side angle side criterion. Side angle side SAS criterion. I repeat, if any two triangles share two sides and the included angle, these two triangles are going to be congruent. They are identical triangles. They have the same shape and the same area. They coincide exactly when superimposed, right? So this is the last of the three statements that I mentioned. In summary, we looked at 8 axioms originally described by Euclid and 3 other statements. They are not axioms, but we'll consider them as axioms because without them we cannot proceed any further. With that, I come to the end of the presentation. Thank you for watching.